Friday, which is wild. I love Alaska.
That's cool. But stay
Literally.
safe. Yeah.
I mean, I went hiking in like early September, and some other friends who were on a similar trip and stayed at the same base camp and me got snowed out of their summit attempt on another way more technical thing that I'm not at all capable of doing. But like it was like September 2nd or something like that. And I was like, what's going on? Is this normal?
Who knows? Okay. Got a pretty good group, so I'm gonna slowly get started as per usual. So today we're going to be talking about, oh, see, one more person joined, perfect. Good thing I start slowly. Today we're going to be talking a little bit about how we can determine different properties of a galaxy based on the strength of different emission lines. So last class we looked at how we might use emission lines to measure rotation and what that can tell us about galaxies. Today we're going to think about just other general properties we might be able to measure by looking at the strength and size of emission lines. So just as we get started, I wanted to do a little review based on what we covered last week. So this should look semi-similar to the rotation curves that you got last class. This is the kind of rotation curve from the paper I pulled our data from. So for NGC 7331, which was the galaxy we were looking at, if yours looked flatter, that's fine. That is because you were using my janky ellip app code, which has something wrong with it, and I don't know what, but it's close. So this should look like similar values to what you got, just maybe a little bit of a deeper indent in the center. If you were using photutils, then this should look very similar to what you got. But I wanted to start us just with a little review question. So if you were using this 21 centimeter line to measure the rotation of NGC 7331, what could you learn about this galaxy based on the rotation curve? So specifically, like what part of a galaxy are we measuring rotation for when we look at the 21 centimeter line? And what properties can we get from that? So either shout out or put in the chat what we can learn from rotation of the 21 centimeter line. Yeah, so getting the mass of the total galaxy. And that's because our 21 centimeter line is coming from that atomic hydrogen, which is pretty well distributed across the disk. So measuring rotation in the 21 centimeter line, we're seeing the whole disk. So we're seeing the whole mass of the galaxy based on the rotation of this line. If we were instead to look at really specifically at the rotation of the central region, we might be able to get a supermassive black hole mass, but that's trickier to do because of resolution issues. But we can do it for a few galaxies. Okay. Any questions left over from last class before we dive into new material? Cool. So today we're going to focus on other things we can learn from emission lines besides just looking at the kind of kinematic properties of a galaxy. And so to get started, I wanted to first look at what emission lines might look like, but also start with a kind of silly quote that was from one of the readings I did about measuring emission lines from galaxies. So it was to try to make a model of an atom by studying its spectrum is like trying to model a grand piano by listening to the noises it makes when it is thrown down the stairs. So therefore, trying to model a galaxy by studying its spectrum is like modeling an entire symphony orchestra from the noise it makes when falling downstairs. So as we measure galaxy spectra, it is crucial to understand that any model we use is going to have a lot of limitations and is only going to be valid in certain conditions. So this is the information we have from galaxies. It's emission lines and fluxes. So it's what we've got, and we're going to work with it, but just know that this is all going to be kind of hand-wavy, a little approximation-y as we go through. So with that in mind, let's start thinking about what we're measuring when we actually are measuring emission lines. So first we can I'll get to the values that I have over there in a second, but first I just want to point out that emission lines have a few different parts. So if our gas was completely still, there was no motion, and quantum mechanics was not exactly a thing, so different, we would expect our emission line to just be one single straight peak at the wavelength, at the energy of the transition that we would expect to see. Of course, that's not the case. The gas will be in motion, so there will be Doppler broadening, which will cause the emission line to look more like a Gaussian structure. So there's a part of the emission line that will be modeled really well by a Gaussian, caused by the Doppler broadening of the line just based on the motion of the gas, assuming it's moving with a Maxwell-Boltzmann speed distribution, you'll get Doppler broadening of a line. Also, because of quantum mechanics and the uncertainty principle, energy levels in an atom are slightly fuzzy, which means that instead of getting a real nice one energy, one wavelength for each energy transition, there's also something called a Lorentzian profile, which broadens the line slightly. So that's this red line here is showing a Lorentzian profile. The sum of these two things is going to be kind of the model of our emission line, and those are called often Voigt profiles, are used to model emission lines. For galaxies, for the most part, we can kind of ignore the Lorentzian broadening and focus instead on the Gaussian emission profile, so the Doppler broadening. That's going to be most of what we're seeing. The Gaussian broadening is also kind of the dominant broadening source around the center of the line, which is going to be the part of the line that is easiest to observe. So typically when we're measuring emission lines from galaxies, it's pretty okay to use just a Gaussian model to fit our emission lines, which is what we're going to do in this class. We're not going to worry about the Lorentzian wings. We're going to instead just focus on the Gaussian part of the emission line, which is a fairly good approximation, especially when the wings of your emission line are often going to be the messiest parts because they're the lowest flux. So they're going to be, the signal to noise ratios will be larger there just because the signal is lower. So noise will be more of a factor. And there might be other sources in a galaxy that are emitting light at those wavelengths at either side of your emission line, which will make it even harder to measure the Lorentzian broadening. So by kind of ignoring that part and focusing instead on the Gaussian profile of the line, we can find the intensity of a line by fitting emission lines to Gaussians. Oops, sorry. So once we do fit our emission line to a Gaussian, there's a few different properties we might be interested in. So the first thing to think about is just the difference between the rest wavelength, lambda naught, and the actual observed wavelength, because pretty much every single galaxy in the universe, with a few exceptions, like Andromeda, is moving away from us because of the expansion of the universe. We expect every emission line in a galaxy to be redshifted. So we can use the difference between the rest wavelength and the observed wavelength to find how fast a galaxy is moving away from us. We can also measure the intensity at the peak of the emission line. That'll give us some information about how bright the emission line is, how strong that emission line is. You might also be interested in the full width at half maximum. So the width of the line at half the peak intensity is a full width half maximum, which that'll give you some information about the Doppler broadening of the line, so how fast the gas is moving. Sometimes you'll also see the half width at half maximum, which is literally just the full width divided by 2. So is what it says on the tin. But either way, that's a way to measure the motion of the gas for whatever part of the ISM you're looking at. The last thing that you'll typically see measured from emission lines is the intensity, which is going to be the integrated flux underneath the emission line. And this is typically, instead of actually measuring all of the flux values and adding them up. This is typically done by fitting a Gaussian and then integrating underneath the Gaussian, because that's going to take out any noise in your observations, and the Gaussian is going to be kind of what we expect to see anyways. So we can get the full intensity of a line by fitting a Gaussian and integrating underneath that Gaussian curve. So just kind of as a summary, we have our emission line. It's going to be both a Gaussian and a Lorentzian, but we're going to focus on the Gaussian part because that's going to be more important in galaxies. Once we measure it, the properties of an emission line we might be interested in are the intensity, so the area under the curve of the emission line, as well as the full width half max, which will tell us about the Doppler broadening, and then the actual peak wavelength, which will tell us about the redshift. So before we get into what we can do once we have those measurements, does anyone have any questions about that? Okay. So once we have some measurements of emission lines, we can determine different things about the conditions of the ISM in a galaxy. So depending on what you want to look into, you'll use different emission lines to get conditions like the density, the pressure, the temperature, what the source of ionizing radiation is. This is also, we talked earlier about when we're doing those star formation rate measurements that I'm obsessed with. One of the ways you might do this is by measuring the H alpha line. So that would be using the strength of the H alpha line to get an idea of how many O and B stars there are, how many young stars there are, to find the star formation rate of a galaxy. So that is another spectral line diagnostic. Very typically, instead of using just the single line, you'll use a ratio of emission lines, because that will give us further information about what's happening inside of a galaxy. And these diagnostics will either be determined theoretically or observationally. So you can either pour a lot of physics in and figure out what you expect to see and then use that to assess what's happening in a galaxy. Or you can go out and get a ton of observations of emission lines and plot them and separate them by different galaxy type and use that to come up with a diagnostic tool. So for example, this diagram, whichever direction it is for you, is called the spoon fork diagram. So this is, at least by my advisor, but it's a diagram made by Henrik Spoon. So this is from Spoon 2008. And it looks sort of like a fork because there's kind of a tine here and a tine here and maybe a tine there. So that's why it's called the spoon fork. But based on looking at the strength of a PAH feature, so kind of an emission line-ish, and the strength of a silicate feature, he was able to separate a galaxy by its different types. So AGN galaxies, galaxies that have a dust-enshrouded source of emitting light, and then star-forming galaxies. So this is one where he went out and got a lot of observations of the strength of the PAH features, as well as the strength of the silicate features, and then noticed that when he plotted them, different types of galaxies fell in different quadrants on this graph. So that's one way we can use emission lines observationally to separate the types of galaxies we're looking at, which is going to be useful, especially if you're looking at like high redshift galaxies where you can't actually observe what they look like. They just look like little smudges. So if we can measure their spectra and get the strength of emission lines, we can figure out if they're more similar to star-forming galaxies or AGNs. Before we get into that though, we're going to do a bit of physics, and I'm going to stop my share for this for a second so I can instead get a whiteboard, and we can do this. I can attempt to do this by hand first, and then I will, then we'll kind of talk through it as well. So one of the ways, this is going to be my kind of hand-wavy version of using theoretical physics to derive what we expect to see in emission lines. So we're going to see how this goes. But if we have an atom, so this is going to be the nucleus of our atom with a few energy levels. So I'm going to call this energy level I and energy level J. And as electrons bounce between these energy levels, we would expect to see light radiated out in an emission line. So that's my beautiful model, doing my best to draw with a mouse. We can do some physics to kind of figure out how strong we expect this emission line to be by modeling the collisional excitations, de-excitations, and spontaneous de-excitations. So if everything is balanced, we'll expect the excitation rate, so the rate at which electrons are bumped up from I to J, which I'm going to be calling Ri to J, is going to be our excitation rate. And then we'll also have de-excitation rates when we move from J to I. So Rj to I will be de-excitation rates. So we're going J to I, so it's de-exciting, and we would expect the strength of an emission line to be proportional to the rate at which electrons are moving between those energy levels. If our ISM is fairly balanced, we expect the rate at which excitations are happening to be approximately equal to the rate at which de-excitations are happening. And we can make some models, we can use some physics to predict how frequently we expect these different things to happen. So for excitation, we expect excitation to mainly happen when free electrons or free hydrogen atoms bump into this. So there's going to be collisions with free electrons bumping into this that will cause both excitations as well as de-excitations. So we can write our collisional excitation rate is going to be Ri J. I'm going to call it collisional. Is going to be equal to the density of electrons, which are bouncing into our ion, the density of the thing actually doing the emitting, times the density of the thing doing emitting, and then times the collisional coefficient alpha. So this is going to look somewhat similar to some of the math we did when we looked at the Stromgren sphere radii, but now we're kind of thinking more generally, not just hydrogen. This could be any emission line, any element. So that's going to be our excitation rate equation. Our de-excitation rate equation is going to have two parts. So there's going to be spontaneous de-excitation, which is without a collision, the electron falling down from J to I by itself. And that's going to be equal to the number of atoms with an electron in the J energy level, so Nj, times something called the Einstein coefficient, which is just some value that has some physics in it that tells you the likelihood of spontaneous de-excitation. And so I'm going to label that with an S, because that's going to be my spontaneous de-excitation. We can also have collisional de-excitation, when electrons bump into our or not ionized, sorry, our higher level particle. So our atom with an electron in the J level gets bumped into by an electron and de-excites, and that's going to be equal to the number of atoms with an electron in the J energy level times the number density of electrons, since if you have more electrons, you're more likely to have things bouncing into you. And then times something called beta, which is similar to alpha. It's the collisional coefficient for de-excitations, and it is also, sorry, that should be a capital T. It's dependent on temperature, just like alpha is dependent on temperature. So if we're back in our kind of semi-stable ISM where we say that collisional excitations are equal to the de-excitations, we can rewrite this as n, our number density of electrons, times the number of atoms with an electron in the ith energy level, times our coefficient, is equal to the spontaneous de-excitation rate plus the collisional de-excitation rate. So now what we can see, if you can read my bad computer handwriting, is that by pulling out this Nj, we can write a ratio of the number of atoms with an electron in the ith energy level to the number of atoms with an electron in the jth energy level should be equal to Aj plus Ne times beta divided by Ne times alpha. So the number of atoms with an electron in the ith energy level divided by the number of atoms with an electron in the jth energy level is dependent on the temperature and the electron number density for the most part. There's also these alpha, beta, and this A are going to be things that we can figure out using physics, using quantum mechanics, and whatever model we're looking at. So this is why we tend to use ratios, especially if you're using the kind of theoretically derived emission line properties, because we can get a ratio of emission from electrons in the ith level and a ratio of an emission line from electrons in the jth level, and we can relate that to electron densities as well as temperatures. So that's my hand-wavy physics of why emission line ratios can be used to get densities and kind of temperature conditions in your ISM. So unless I hear any screams, I'm going to stop this share and go back to my PowerPoint. So, or unless if people have questions about that kind of derivation-ish. Assuming things are all right, so I'm going to stop that and go back to my PowerPoint. Okay, so most of the text here is just kind of words through what I just showed in that derivation. And then again, the ratio of an emission line from an electron in the jth level and an emission line from the ratio of an electron in the ith level is going to be related to the density and temperature of the ISM. Because we can kind of measure temperature by looking at the Doppler broadening of a line, we're going to usually use these ratios of emission lines to get at the density. If we know the density and temperature, you can also get an idea of the pressure just by using the ideal gas law. So that's how we get these theoretical measurements of galaxy conditions based on ratios of emission lines. Typically, as an observational astronomer, I let the theorists do that, and then I just take their models and plug in my values to get actual conditions, because getting the actual models is kind of a mess. So once you have your two emission lines, you can get, mostly the thing you're going to look at is your density in your ISM. This does rely on a fairly massive assumption that the galaxy you're looking at or the region you're looking at is going to be at a constant temperature and density throughout your entire region, which is never going to be true. But that is, again, kind of the best we can do with the resolution we have. And then it's also going to, any of these ratios are also going to be dependent on metallicity. And that's because most of our cooling lines, so most of the like the C+ and the O1 line that we talked about when we looked at energy balance in the ISM, are going to be those metals. So carbon and oxygen are metals when you're an astronomer. So more metals means more cooling, which means lower temperature, which is going to change the emission line ratios we expect to see. But once you kind of have an idea of the conditions in your galaxy, the temperature and the metallicities, you can use your emission ratios of emission lines of a single atom or a single ion of that atom to get at the density. So the reason why we want to use ratios of one element, one ion, is because back in that hand-wavy physics I did, we had that Ni over Nj, yeah, okay, was what was proportional to N. I called it Ne. So we want to look at the same species, the same ion, because then we know that we don't have to deal with differences in composition in a galaxy. So there's going to be the same amount of N2 and the ratio, so there's going to be the same amount of singly ionized nitrogen. That ratio will only depend on the density. So this ratio here, for example, if we're dealing with the ratio of these two nitrogen 2 lines, we don't have to worry about composition. We don't have to worry about the amount of energy needed to ionize nitrogen, because we're looking at two lines of the same ion. So the only thing it should be dependent on are the temperature and electron density conditions within the gas. So that's what this graph is showing, is a few different emission line ratios that we might use to actually track density in the ISM. So the nitrogen 2 one is this dotted line here. There's also one for sulfur 3, so this blue line, one for neon 4, and then one for oxygen 3. So these are all far infrared tracers, because I work with far infrared data, sorry. But the important thing to notice is that there are optical versions of this as well. I just have typically worked with infrared tracers. The nice thing about working with infrared is, again, you don't have to deal with dust extinction, which is great. But the other thing is, as long as your two lines are at least semi-close in wavelength, both should get about the same amount of attenuation from dust. So you don't have to worry about correcting for dust attenuation if you're looking at a line ratio and both of them are getting attenuated. So that's a really nice thing also about using line ratios. As long as you're looking at similar wavelengths, which all of these are in the kind of micron area, so they're all far infrared lines, you don't have to worry about dust attenuation. You can just actually get these measurements and not correct for extinction at all. Another thing to point out, though, is that all of these ratios are only sensitive to certain conditions in the ISM. So depending on where you're looking, what you expect your density to be, you might target different lines. So for example, if you are using the sulfur-3 ratios, which is one of the easier ones to see, so this blue line, and you have a density of 1 to maybe about 100, your ratio of these two sulfur lines is going to be almost constant. So using sulfur-3, if you're in a part of the ISM where you expect densities to be from 1 to 100 per centimeter cubed, your number densities to be 1 to 100 per centimeter cubed, using sulfur-3 is going to be really useless because it's going to look the same no matter what you're looking at. So you're not going to get good resolution in your density if you're using that line. But if you're looking at conditions where the density is going to be maybe 100 to about 1,000, there's a huge range. Sulfur varies a ton in this range. So it would be a really good tracer of the densities in maybe more like the molecular gas in a galaxy where things are denser. So we expect to actually end up in this part of the emission line ratio area where it's sensitive to the density. The other thing that's going to kind of help you choose which emission line ratio to use is the ionization potential of the different lines, which is what is kind of being shown over here if you can read it. So for example, because nitrogen is the one I know the best, that's what I'm going to focus on. In order to get singly ionized nitrogen, you need wavelengths of light, you need photons with 14.5 electron volts of energy. So nitrogen has an ionization potential of 14.5 electron volts, which means we're only going to get singly ionized nitrogen, or N2, in regions where hydrogen is also ionized. So because that's above 13.6 electron volts, 14.5 is greater than 13.6, you can only use the nitrogen line if you are in the ionized phases of the ISM. So depending on what phase you want to look at and depending on what you think the density conditions are going to be, you might use different ratios of emission lines to get at your density. So that's the first thing we can trace using emission lines is density, which also gives us an idea of pressure. Does anyone have any questions about that?
Why is it critical density on the y-axis? I'm assuming it's not a flat thing, is it? Is it a flat thing?
So critical density, these are two separate plots. So this over here is line ratio. So this y-axis is line ratio. Critical density is what I'm going to talk about next. And that's another property of emission lines. I forgot this was my next. So good question, leading me right into what I wanted to talk about next. So another thing that will potentially influence your measurement of density is making sure you stay below the critical density for your emission line, which the critical density is the density at which spontaneous and stimulated emission are equal. So what that means with our equation is that, I can't type that, I have to do my bad drawing, okay, is that our R J I collisional is going to be equal to our R J I spontaneous. So this is the density at which that is true. Collisional and spontaneous emission are equal is called the critical density. Above this critical density, we no longer get more emission with higher density conditions. And that's because we've essentially reached a point where all of the collisions that are going to happen are happening. You can't get more stimulated emission from the gas by adding in more electrons, because anything that's going to be doing this transition is already doing it. So above the critical density, intensity does not increase with density. So you can no longer use that line to find a density in the gas. So that's why, on this previous graph, one of the other things they're showing is the critical density, because that's going to be one of the things that limits the conditions in the ISM where you can use any specific ratio of emission lines. So yeah, so critical density is where spontaneous and stimulated emission are equal. So we can no longer dump more electrons or whatever your collisional partner is into the ISM to get more more de-excitations, which will produce our emission line. So higher densities no longer mean stronger emission lines when you are above the critical density. And I should also really quickly point out that throughout these examples, I've been using electron number density, which assumes that our collisional partner is going to be electrons. That's going to be true when we're in the ionized phases of the ISM, but it's not going to be true when you're in the neutral phases, when there's more neutral hydrogen. So that doesn't have to be an electron density. It's only going to be an electron density in the ionized phases. In the neutral phases, it might be a hydrogen density, which is, the math still works. It's whatever your collisional partner is, whether that's electrons in the ionized phases or hydrogen atoms in the neutral phases. Or maybe molecular hydrogen if you're in the molecular gas. Sorry. Any other questions about density stuff? Okay. Sorry, this figure is going to look kind of small. I was going to change it and then I didn't. But the next thing that we can think about measuring using ratios of emission lines is the something we call the ionization parameter of a galaxy, which is typically represented by this by U. So U is equal to the ionization parameter. U is a dimensionless quantity representing the amount of ionizing radiation. So essentially what that means is that U tells us how much radiation in a galaxy is able to ionize hydrogen. So anything with any radiation with energy above 13.6 eV, electron volts, sorry. This is pretty much just FUV radiation. So a lot of times also U is just the radiation from 6 to 13.6 electron volts. So a value that's semi-related to G0, which was the amount of ionizing radiation in PDRs, but U is a little bit more general. It's not just for PDRs, it's for galaxies in general. We can get it to be dimensionless by dividing it by the value of the amount of FUV radiation around the sun. So you take that number, divide, and compare the amount of ionizing radiation around the sun to what you're measuring in a galaxy to get this dimensionless quantity, which is used to just find the number of ionizing photons in a galaxy. So typical values of U tend to range from -3.2 to -2.9 when we're looking in log space, and that's typically how this is shown. So typically you'll see U displayed as a log, and then you'll see values of -3 to -2.9, with higher values being more ionizing radiation. So more ionizing radiation, U is higher. There's more FUV radiation in your region. Measurements of U, instead of using the same ion, we'll use ratios of two different ions of the same element. So for example, the 5007 angstrom line of doubly ionized oxygen and the 3727 angstrom line of singly ionized oxygen. We use these different ionization states of the same element because More ionizing photons means there are going to be more doubly ionized oxygen compared to singly ionized oxygen. So U must be larger. You want to then also use the same element because then you don't have to worry about abundance issues. So you don't have to worry about metallicity. You're only measuring one element. There's no issues of different composition within your galaxy, complicating your measurement of ionizing radiation. And then again, you want to use similar-ish wavelengths when possible. So both of these are going to be optical emission lines. So they will both be attenuated by dust, but they should both be attenuated by dust by about the same amount. So it's okay to use two of the same ratios and not have to worry about correcting for extinction when we're looking at these ratios of emission lines. So this is just showing this graph. Sorry, it's small, but this is showing measurements of U for a few different elements. So we've got carbon up here where we have doubly ionized a ratio, so the log of the ratio on the y-axis versus what log of U will be on the x-axis. So if you can measure the emission line strengths of these two lines of doubly ionized carbon and one line of singly ionized carbon, then you can find where your galaxy is on this x-axis and get an idea of the amount of ionizing radiation. This paper was also looking at how these ratios were dependent on metallicity. So metallicity is also a factor. It's best if you know that going into it, because then you can better predict what you expect your measurement of U to be based on your ratio. So these are just, we've got a carbon one, a silicon one, aluminum, I think, oxygen, sulfur, neon, another sulfur, and then a nitrogen one as well. So lots of different ways to measure this line, kind of mostly going to be dependent on what part of the spectrum you're observing your galaxy in. So are you looking in the optical, so you're going to want to use optical lines, or are you looking in the infrared, so you should use infrared lines? Any questions on that? The next thing we can think about measuring from emission lines is the composition of your galaxy. So typically we do this by measuring metallicity. Since we kind of talked about metallicity last week, I'm going to kind of jump through this fairly quickly. Usually when we measure the metallicity of a galaxy, it's by using this, 12 plus log OH version of metallicity, because oxygen is going to be one of the more prevalent elements in a galaxy. There's not going to be a ton of iron, so trying to measure the Fe over H ratio is going to be more difficult, just because the iron emission lines will be weaker than the oxygen emission lines. So we typically see this 12 plus log OH when we're looking at galaxies. And it's just the emission line strengths of a few oxygen lines divided by the emission line strength of the H beta line, which again, I think we talked about last week, 2 weeks ago. Measurements of the metallicity of galaxies have shown us that there's a relationship between mass and metallicity, which is kind of cool. So that's what this graph is showing here. Galaxies with higher metallicities also tend to have higher stellar masses. And that's probably because of differences in star formation histories. So dwarf galaxies tend to have really low metallicities, whereas more massive spiral galaxies and elliptical galaxies have higher metallicities. Probably because the larger galaxies have just had more star formation in their history, and therefore have been enriched by these cycles of star formation, dumping heavier elements into the ISM. Another kind of fun thing about this paper is that it also shows how this relationship changes with redshift. So in really low galaxies, or really high redshift galaxies, the gas has not been enriched yet, so they're lower metallicity until we get up to now when we're using SDSS to see galaxies at now. We're higher metallicity, but we still see this kind of same mass metallicity relationship no matter which galaxies we're looking at. The last thing we're going to focus on when we look at ratios of emission lines is the ionizing source in a galaxy. So this is one that we can only really get by looking at observations. So this is not, there's not so much theoretical physics here. This is just something we've realized that we can look at ratios of emission line to figure out where the ionizing radiation comes from in a galaxy. So this is distinguishing between galaxies where that are dominated by star formation, galaxies that are dominated by a central AGN, or galaxies that are dominated by shock-heated gas. Maybe they've recently gone through a collision. So in order to do this, you use ratios of lines at similar wavelengths, but with different ionization potentials. So if you're looking at lines of a similar wavelength, there's similar amounts of absorption, but different ionization potentials means you need different amounts of ionizing radiation to create the ions. So these are the only lines where we're typically looking at not the same elements, not the same ions. Instead, we're looking at different elements with different ions, different ionization potentials. So the ones we're going to focus on are going to be H beta and O3. So two lines that are fairly bluish-ish, green, I guess more green, I should say. And then H alpha and this N2 line. So two lines that are pretty much right on top of each other over here in the red. So really similar wavelengths, but we're looking at neutral hydrogen compared to doubly ionized oxygen and singly ionized nitrogen. With those lines, you get something called a BPT diagram. So looking at the ratio of those two lines of the two ratios of four lines, I guess, we can get an idea of what the ionizing source in a galaxy is. So BPT stands for Baldwin, Phillips, and Telrovich, which are the people who came up with this emission line diagnostic tool. And they found that they could separate AGN galaxies or Seyfert galaxies from star-forming galaxies and liner galaxies or low ionization nuclear region galaxies, which we think might be a type of low luminosity AGN based on these two ratios of emission lines. So these was our red emission lines of nitrogen and hydrogen, singly ionized nitrogen and hydrogen, neutral hydrogen, and then our ratio of doubly ionized oxygen and H beta, so the Balmer beta transition in hydrogen. So just to kind of show this again, we've got our similar wavelengths, so H beta and O3, and then H alpha and N2, but really different ionization levels. So the ionization potential of nitrogen to get to nitrogen 2 is 14.5 electron volts, and the ionization potential of oxygen 2 to get to oxygen 3 is 35 electron volts. So changes in the amount of ionizing radiation and where that, how much energy that ionizing radiation actually has will change the ratios of these emission lines, moving where a galaxy will fall on our BPT diagram. And that is what we are going to do today, is we're going to measure emission line ratios to figure out where on a BPT diagram NGC 6946 falls. So we're back looking at my favorite galaxy. So that's going to be our goal for today. This is another one that, so the good news is no more photutils. Everyone's using the same thing this time. So in your assignments, this is one's called Measuring Line Fluxes. There's a notebook, which if you did download it early, it's been changed in the past hour to be a little bit more explicit. So you'll want to re-download it. Again, sorry. And then the spectrum of NGC 6946 is this text file here. And then there's also some data from SDSS that we're going to use to plot a BPT diagram. So this is from the Sloan Spectra Survey. When you get that going, your goal is going to be to add NGC 6946 to a BPT diagram. I've already fitted one line for you. So I've made a BPT diagram. Sorry, this is just, there's a ton of information in that SDSS file. So this is our BPT diagram from SDSS, which I've graphed. There's some errors because we're working in log space, so we can use NumPy to get log 10 of the two ratios of our emission lines. And then Python gets angry because there's some log 10s of negatives or something, and it's like, I can't do this. But that's fine, we can ignore that because we still get a nice plot that has the shape we expect. I then also gave you the optical spectra of NGC 6946 from a paper by Lira, and plotted that. So here you can see we've got wavelength and flux in our file, so we can just use those to pull out data. We're then going to use a Gaussian, a one-dimensional Gaussian to fit our emission lines. The good news is fitting one-dimensional Gaussians is easier than fitting two-dimensional Gaussians, so this should be less painful than your star fitting. It should actually work every time. So that's positive. But in order to help out the line fitter a little bit, we're gonna have to cut out our data around each line we wanna work with. So I've done that for the H alpha line. I've just kind of grabbed the data, 10 angstroms on either side of the H alpha line, which is at 65, 63. I didn't worry about redshifting because NGC 6963 is about 3 megaparsecs away. Sorry. So it's close enough that yes, it is redshifted, but it is redshifted only a slight amount. So we can pretty much ignore that and be okay. So you can always just kind of assume that your rest wavelength is approximately the rest wavelength of the line. So then I also measure the continuum flux of the galaxy. So that's going to be what the emission is on either side of this. So I want to find this so I can subtract that continuum flux and make sure I'm only measuring the flux of the emission line. So I find the continuum line flux and I subtract that. And then to help out the fitter, I'm also going to center my line around 0 instead of around the actual emission line. So then we run our fit and we get a nice fit of an emission line, and we can use properties of Gaussians to integrate and get a flux value for our H alpha line. So that's what I have printed there. So your goal is going to be to replicate that for the H beta, N2, and O3 lines. So you can put NGC 6946 on this BTP diagram. So any questions before I release you to get that going?